Okay, so today and maybe some of next class, I'm going to be talking about statistics for computer science experiments. So statistics is an important part of any experimental science, and since we've already had some talks on about computer science is an experimental science, you need to understand at least some very basic statistics. Okay, and I will tell you, the bad part is when you read a number of computer science papers, maybe even the majority of them, you won't find all of them doing statistics. Okay? And there are times when you don't need statistics, but almost all of those papers would actually be much better if they actually did the statistics. The bad point is that very often the papers wouldn't be publishable if they had the statistics, because the results would say, yeah, our algorithm actually isn't actually better than somebody else's. So people tend not to do that. You should in fact become aware of when it seems like results are sidestepping the statistics, because it's often the sign that there's something deeper wrong. You want to try and find a way to use statistics to tell your story. On the flip side, as implied by this cartoon, you have to be a little bit careful with statistics, because the saying is there's lies, damn lies, and statistics. And depending on who, doesn't matter who it came from, it's actually, guy begins with a D now, I forgot his real name, but is it in here? No. Anyhow, so the problem with statistics, Disraeli, yeah. Well, actually, it's now disputed whether or not Disraeli is the first guy who said it. But there's multiple people who have had different points in time. But the real thing about statistics is, if I misuse them, I can sound very scientific and be very wrong. Right? So statistics can be misused, and there's actually a whole set of talks and things you can find out about misusing statistics. And to be honest, graphics has the same thing. I can mislead people a lot, right? But there are very careful phrases that people sometimes use. And so it's not just that you want to use statistics, you want to learn how to use them right, because you don't want to mistakenly lie with statistics. I'm not going to teach you how to intentionally lie with them, although I will point out some of the most common ones that people use, because you should be aware of them, because they're common mistakes. It's hard to tell if they're doing it intentionally or if they just did something wrong. But just as a first example, how many of you have heard the phrase 4 out of 5 dentists, whatever, okay? Now, that's not a statistical statement, but it is, right? It's saying that 4 out of 5. Now, the question is, does that mean if I surveyed exactly 5, 4 out of those 5 said that, or 4 out of every 5? How do you as a person interpret the phrase 4 out of 5? Most people will interpret 4 out of 5 as 4 out of any 5. But in that particular thing, it was 4 out of exactly 5. And they were sued because somebody else did a survey and it wasn't 4 out of 5 in a large population. So if I surveyed 50, I'd expect 40 dentists to recommend it. But the number was closer to 25. But they surveyed 4 dentists in the hometown of the company. Bias sampling is a big problem with statistics. It doesn't really matter. I mean, that's just an example, but literally they were sued. But in court, it's like, no, we didn't say what 4 out of 5. Here's the 5 we surveyed. These 4 said it was. That's good enough, right? That's where statistics can give a line. It's also important, but sometimes a little bit dangerous when you're talking about doing statistics and experimental design, that you actually are very clear about what are the experimental conditions, and you try and make them meaningfully fair, right? So this cartoon is about the fact that if I'm testing the ability to solve puzzles underwater, cats are not very smart, right? They don't really function very well underwater. Octopuses do fine, right? That doesn't mean that cats aren't smart. It just means that experimental condition was bad for them. So it's not enough when you hear about statistics to say, here's what the statistics say. You have to understand the way in which the experiment was run. That really isn't statistics, but you can't interpret the statistics without it. That's in fact where the 4 out of 5 doctor example is the same thing, right? How they measured 4 out of 5 is an important part of that statistic that 4 out of 5 doctors recommend whatever the toothpaste was or whatever it is. Okay. Now, the other part which is related but different, and I want to bring this up because I see a lot of this, when you're dealing with experiments and writing papers, you should understand good scientific process. you should know when you're doing your experiment whether or not you should be reporting 1 significant digit, 2, 3, right? So if I run 10 runs of a program and my computer outputs 3.01, 3.10, whatever, up to 3.23. If I get 10 numbers that were printed on my screen with 3 digits of decimal precision, I shouldn't report a runtime of 3.14159. Right? That has too many digits. If I average 10 numbers of 3 digits, the most significance I can have is 4. Because I actually put in 10 numbers of 3, I get 1 extra digit from averaging. But in general, I should probably be actually reporting. Now the next question is, how sure am I about the 3.1, that last digit of my experiment? How stable is that number? Maybe I should be reporting 3.1 plus or minus 0.05. If 0.05 is a standard deviation, we'll talk about that in just a second to be clear, right? Or maybe just, if I don't know the standard deviation, or if I didn't bother to compute it, then I should say something like 3.1, or maybe 3.10, but not much more than that, okay? But I will see papers where they talk about things, and they will show me 7 digits. Why? Because that's what Python printed out for them, right? The default for Python is to print 7 digits. It doesn't mean they're all meaningful. So you want to be a little careful and show good science part to go with it, which is actually related to statistics. You shouldn't be showing me digits in your numbers that are statistically meaningless. Right? If they don't have statistical meaning, why are you showing them to me? Now, formal statistical testing is too annoying to figure out the number of digits, but you can use some basic rules of thumb. The accuracy with which you measured things is the accuracy with which you measured the least significantly in all of your data should drive what you limit your accuracy. So if I'm looking at all these numbers, then maybe here I have a bunch of numbers with 2 digits. 2 digits is all I should do. And maybe I could run down to 1, but you can have 2. Okay, so now when we talk about performance measures for an algorithm, okay, there's lots of things you will see in a paper. You will see, by far the most common is people will talk about, well actually, the most common is actually probably this thing over here. There's just a number. They didn't run it more than once. They just said, here's my performance. Okay, that's not really the best kind of thing, right? Maybe what I really want to have is having a mean, okay? So here I might have, instead of just a number, I might call that number the mean. I might take 10 runs of my program and compute the average accuracy, the average speed up, whatever, the average, whatever my performance metrics are, okay? And when I'm doing that, ideally, in fact, I don't even want to just say, here's the mean, which is better than just saying, here's a number. I really want to give a range. And ranges can be min and max, plus or minus a standard deviation. There's a lot of reasons you could have it, but you want to be careful to think about what error bars are. So if I go back to this and I were to say, is this algorithm, assuming performance is that lower is better, is this mean circle better than the triangle? If you just saw on a paper and they said, look, my mean error is lower than their reported diamond error. Is this algorithm better? Error? Well, I didn't show you the errors yet. So this is, I'm going back to sort of why the errors are important, right? If I were to if I'm just asking you, is the mean, accurate errors here, is this mean better than the triangle?
Without more information.
Without more information, but lots of papers will imply it. They'll say, look, my performance is better. Okay? As soon as I show you error bars, now the answer becomes, it's not so easy to answer. If these vertical bars represent standard deviations, and I'll talk a little bit more about that in just a minute anyhow, plus or minus that standard error. Now the errors between these two algorithms.
Well, you want the one on the left, that's precise versus, I mean.
So the one on the left versus your left or my left, but that's a different
Oh, my left, the triangle.
This is the triangle.
Is precise, and I would take that every time.
So what's funny is the answer depends on what you want to do with it, but the statistical answer between these two is you can't tell, right? With the experimental data here, it's not clear that one is better than the other unless, as Joseph said, you use what's the size of the variance to say what the answer is. But if you want to decide that the size of the variance is the measure you're interested in, then you'd have to run another experiment to measure the variance of the variance, right? Because this is now just one measure of the variance. I'll estimate what that. I'll also show you there's this other variable here called median, and you'll find some papers that talk about, instead of reporting means, they report medians. Does anyone know why would I prefer to use a median over a mean?
Extremities.
Right, so the mean, if I have a bunch of numbers, okay, the mean of this sequence, I don't know, 5,000, 4,900, or 4,800, or whatever, right? The mean is add them all up and divide. The median is 7, right? You sort the numbers, you take the middle. The mean, the average, is very sensitive to outliers. One number here, if I make this number add a couple more zeros, right? Then the mean just shifted from 5,000 to 500,000, or somewhere, whatever that number is. Maybe it's from 1,000 to 100,000. Right? One number has a large impact on the mean. One number has almost no impact on the median. So if I'm dealing with data that is very noisy and there can be lots of extremes, then I might want to use medians instead of means.
I always thought it was linear versus nonlinear. Right? When you have a linear representation, the mean is fairly accurate, usually. But when you have an exponential or something like that, then all of a sudden you're
So not necessarily the case, because if I do linear, right? If I do linear and I make my linear function is 4 times these, right?
yeah, right.
It's nice and linear, but the sampling here has the problem, right? So things like the average American salary is quite different than the median American salary, because there's some people that make ridiculous amounts of money. Right? And when you make $1 billion a year, like Bill Gates does, and there's only 300,000 people, right? His salary is greater than, what was it, one of the numbers right recently was like, the wealth of the top, the Forbes top 50 is more than the 3/4 of the country, or some like weird number, right? Averages are skewed by a few very big numbers, and that's where they're problematic. And this is where about half of what I'm going to say today has to be taken very carefully anytime you do computer science with very different numbers. And I'll come back to what Joseph said, because this is often another case. Sometimes when I look at numbers, they're outliers because I'm in the wrong number system, right? If I'm actually looking at something and I see data that looks exponential, maybe I should be looking at the log of the numbers. Right? In computer science, there's lots of things where we have choices. I can look at this, I can look at the size of the number, or I can look at the number of digits. If I count the number of digits, then this is 1, 1, 1, 2, 8, right? Now the average isn't necessarily such a bad thing. It's actually still pretty weird because it's pretty far from 1, but it's not as bad. So understanding what is the representation of your data is actually a big part of being computer science, right? We deal with this. So do I represent it in binary, do a log transform? There's a lot of transformations you can do to your data. Okay, if your data is very exponential, that's actually easy. That's a change of basis. Now take the log and work in linear space, and you'll be fine, right? But that doesn't mean it stops outliers. Outliers are separate from that. That's why it's an interesting position. But so first, you want to make sure that your data is in a reasonable range. It doesn't have hugely varying numbers. If it does, a lot of statistics become very complicated. Underlying the bulk of what we're going to talk about for more than half of the statistics lecture is the assumption of Gaussian data. Right? We're going to assume the world is normal. And I actually forgot to put this in the slides, but why do you think so much of what we do assumes the world is normal? Anyone have, do you know what I mean by normal? Gaussian distributions? Why do you think people assume Gaussian? Okay, a couple. Give me a couple.
The normal distribution, we see it a lot in the physical world, in nature.
Okay. Yeah. So in fact, seeing it in nature is an important thing. In fact, one of the reasons. So why Gaussians? Well, one is it's common. But we have to be careful because maybe it's common because we use it a lot, not because it's really there. Deeper than this is what's called the central limit theorem, CLT. How many people know what the central limit theorem is? Anyone not know what it is? Okay, so the central limit theorem is an important part of statistics. And that's why I realized I should have put these slides into it. I assume you've all had some basic stuff, but maybe not. The central limit theorem says that the difference, and I'm going to do a short version of it, the difference between the mean of x, okay, and the sum of x, the sum of x, I equals 1 to n, 1 over n, in the limit as n goes to infinity, and there's a secondary element here, n goes to infinity, converges, no, it's not converges to a normal 0 sigma. Okay? So the central limit theorem, which is why it is so common, basically says that the difference between the true mean of a variable, x bar is a common way of saying the mean, the difference between a mean and the sample population mean, which is the sum of all the data divided by, right, that's our approximation to the mean. This difference is normal distribution with mean 0 sigma standard deviation, right, for almost all ways you can sample x. There's a few rules that have to go with it, but if I take lots of samples over lots of things, the distribution will turn out to be Gaussian. Okay? And if you look at things, there's actually various experiments where you drop particles and you have a bunch of boxes and you watch where they go, right? The tendency is for them to go straight down, but they'll bounce around. You get a Gaussian that comes out of it. In fact, it turns out it's related to this. The process is the mean, is a distribution of how far can something get away from its mean. There's a chance of getting farther and farther away. So the central limit theorem is sometimes used as a rationale for why things will be Gaussian. Okay? On the other hand, the restrictions that underlie this are not as true as we might like them to be. For example, if I flip a coin, okay? Flipping a coin, the mean value, the true mean value of a fair coin is 0.5, and this contributes extremely well. This will converge. After 30 samples, you're pretty close to the mean. Okay? The problem is that doesn't mean that the distribution of the flip of a coin is Gaussian. And this is where people get it wrong a little bit. What's the likelihood distribution? So if I think of a coin as flipping as 0 and 1, the expected value is 0.5, right? That's the mean. Right? But 0.5 is not even an option for the coin. Right? The coin is either 0 or 1. And what I really have, so a Gaussian distribution around the mean would look like this. Right? Roughly, that's a Gaussian, right? The distribution of data values is that, right? And the heights of these two may change a little bit. And this is where people sometimes get confused. The Gaussian doesn't always apply. The Gaussian that underlies this, as I said, this is in the limit, and there's a secondary thing here, which is the sample of this distribution, right, is over many samples of this process. So if I think of this as a process, if I get the mean and I measure this once, the true mean is 0.5, at least theoretically. Sometimes I'll get 0.49, sometimes I'll get 0.51. If I run that experiment with coins 100 times, I will actually get a distribution of the mean that looks like this. But the actual coin flips are always this distribution. So you have to separate the distribution of your statistic, the mean, from your statistic, the actual outcomes. Okay, and when we go to apply statistics, this is really important because lots of things we're going to do are look at the means of our runs. Okay, if I take 50 runs of my program and I look at the mean of that, then this applies. The average of 50 runs of my program applies as long as, and here's where the second caveat, as I said, there's a couple of restrictions here. The restrictions are supposed to be that the samples are independently drawn. Okay? So, if I flip a coin, every flip of a coin is independent of the last coin. Okay? But if I'm running an algorithm, is every run of the algorithm independent of the other runs of the algorithm? Now it's tricky to figure out what exactly does independence mean in terms of what we're doing statistics with in computer science. So normally, if you give a good enough description of the environment, but I will tell you things, and I think I don't know if it was in the experimental design lecture, I think I did. Things like if I want to run the optimizer of my compiler, and I want to test how fast is my compiler, or when you're playing with clocks, okay, the environment variables that are in my environment, my bash shell environment, will affect what my compiler does. And it will affect the timing of various events. And my environment, since my environment's the same, if I do something really weird, I might get a very biased set of experiments. So if I run it 10 times today, and then 10 times tomorrow, but tomorrow I log off, log back in. Or if I run it 10 times on 3 different machines that I think are identical, but turns out they have slightly different installations of software and whatever, then I will get possibly 3 clumps of data that are not independent. So there's a bunch of violations of independence that can occur in computer science. And it's important that you try and make those not be there, but those are the things that will most mess up your statistics when you're not paying attention. So you want to be a little careful for those. So as we talked about doing experiments. So as we've said before, any good scientific should state a hypothesis and then provide evidence for or against it and conclude whether or not it should be supported. And that should really be a precise, explicit statement, and it needs to be falsifiable. All this is stuff we covered when we talked about what's a good experiment. When you want to run the experiments to confirm or refute it, you want to ensure the experiment really tests this hypothesis. So it's important when we start talking about hypothesis testing, you understand what an experiment can and cannot show. Okay? I cannot show in any reasonable experiment that 2 things are equivalent. I can show that 2 things are different, and you'll see how that comes up in a second. But it's very hard to show that 2 things are equivalent. Right? I can fail to show that they're different, but that's a difference which we'll come back to. So you want to sort of design your hypothesis, and sometimes it means designing your experiment. So as you expand your hypothesis, you can have questions, and some of these come from stuff we've already talked about, right? That my technique, my system, my theory is good for task X, okay? That is, whether or not that's falsifiable depends on, is there an independent definition of good for X, okay? So sometimes you can have something for which that is a perfectly good answer. If I'm trying to do something that I want to be able to detect and track something between frames of video, right? Video runs at 30 frames a second. As soon as my algorithm runs at less than 30 frames a second, I can say it's good for real-time video tracking, because at 30 frames a second, if I'm at 26 or at 15, it doesn't change as it's suitable for real-time video because it's always less than the constraint of the time. Okay? That doesn't mean it's the best algorithm, it just means it's suitable for that problem. So if a problem has a natural definition of suitable, if I know that users need a response within 1 second, and I can give them a response within 1 second, then I have an experiment that doesn't have to compare against anything. I've answered the question, is it good for task X? Okay. Those are the simplest, but they're actually not the best kinds of things. So a better test is, it's better than rivals R and Q for task X. Okay, because now I can compare it. And I might say, my time is the same, my memory is less. That's a definition of better, right? My memory is the same, my time is less. You can change definitions. There's lots of things like that. So you can do these according to behavior, the correctness, the quality, some level of coverage, what kind of problems does it apply to, some efficiency, resource consumed of any kind. Any of those can be evidence. And the evidence can actually be theoretical, experimental, or both. As I think I mentioned last time I actually gave a lecture, whatever that was, I am actually a big believer in experimental evidence because I can have a theory that doesn't match reality. Experiments are the only thing that match reality, and that depends how good the experiments are. Okay. So I want to give an example to get through this to sort of put people in the statistics point of view by talking about hypothesis testing. So imagine that we have a criminal jury, and a criminal trial in the United States is a place where you have hypothesis testing without statistics. One of the things that annoys me about things. But so in the trial, you have to decide between two hypotheses. And you all know what I mean by trial, right? So either the defendant is innocent, and the alternative hypothesis is the defendant is guilty. And in different systems of justice, the default hypothesis might be different. In the United States, the null hypothesis, the default is the defendant is innocent until there's enough data to get you to prove the opposite, okay? Until you can prove it's guilty. Now, it turns out that's actually not the most correct statement. In the normal sets of laws for criminal trials, that is the default law. There are various places in civil law where the defendant is guilty until proven innocent. And so we have a whole bunch of things where the burden for me, if I'm a contractor and I'm building houses along the side of a hill, and this is a known place where there can be landslides, I have to prove, if I do some work down here digging in the dirt and a landslide happens, I have to prove I didn't cause it. Because the presumption is if I'm taking dirt out of a hill, the hill might slide. And I'm supposed to know that as a contractor. So it's not always that the default is innocent, but that's normally the default. So depending on where you're in the law, the default might change. But you always have one set of defaults, and then you have to try and change the hypothesis by data. Okay? And when we start, we don't know which is true. We're going to look on the basis of evidence. So in the language of statistics, the convicting a defendant is what we call rejecting the null hypothesis. I sort of said this a little bit earlier. We actually, with statistics, can't prove something is true. We can simply reject something. And this is important, if I reject the null hypothesis instead of the alternative, then we say there's enough data to say the person's guilty. Right? There's enough evidence. But if I don't get enough evidence, I don't leave the default. Right? So I'm not trying to answer the question, is the defendant guilty? Despite the way the phrase gets used sometimes. We're trying to say, is there enough evidence to say they're not innocent? And in the closed world of assumption, and I'll come back to this because my own research gets into this a lot, right? In a closed world, if you have a hypothesis and it's opposite, right? If I'm not H, I have to be not H, right? The null hypothesis. This is an assumption that underlies lots of our statistics. Okay. Unfortunately, it does miss something else as a possibility, right? Which is that there's a third alternative. So if the evidence suggests the person is not guilty, does that mean the person is guilty? That's the way we, as humans, generally interpret it. That's the way our law system works. Okay. There is always the other possibility. The person is innocent, and we simply misunderstood the data, looked at the wrong data. Right? There's a whole bunch of things that go wrong. And we'll talk about what we call type 1 and type 2 errors. So there really are two possibilities. A type 1 occurs when we reject the true null hypothesis. Okay? That is when the jury convicts an innocent person. Right? The person was innocent, and we just used the wrong data, or we misunderstood it, or whatever the bias was. We say that person is guilty, but they actually were innocent. And we try and make sure that that happens very infrequently. So if we think about sort of paying for damages, we would be, this is why in different situations the law is a little bit different. The level of evidence necessary for certain things, you have to have everybody on the jury unanimous, because that's much harder to get than just a preponderance of the evidence makes me feel, right? So, in fact, in jury trials, in the United States, we have beyond a reasonable doubt is the criterion for felony trials, and a preponderance of evidence is what's necessary for most fiscally related trials. And the two are very different, okay? So when we talk about this type 1 error, the probability of a type 1 error, we want to be, in statistics, we'll call that alpha, and we generally want it to be small, generally 0.05 or 0.01. So in a non-statistical test, we have no way of doing probabilities if I'm doing non-statistical tests. But it gives you the idea that, so this is the first error. we convict somebody who's truly innocent. The second error is we don't reject the null. We don't reject a false null hypothesis. Okay, that is the person's guilty and we let them go. Okay, and this is common. This is actually the more common error, and actually the way the American jurisprudence system is designed, it's the way we would prefer to make errors. The two errors are not viewed as equal in the United States. Convicting an innocent person is much worse than letting an innocent person go, or a guilty person go free. Okay, and that's because the penalty of being in jail for a long time compounds that error. So we want to make sure that it doesn't happen. Okay, but you have to be careful in experiments. We'll come back to this from an experimental point of view in a little bit. Very often the penalties can flip around. In a medical position, or in fact, as I said, when I'm doing things like where construction is like doing something that causes landslide, the reason the law for a bunch of those cases turned around is because the penalty for them screwing up is so high. Because if I mess up and I cause a landslide, I could kill people. So it's my job to make sure I'm taking extra precautions, and I have to be able to prove I didn't cause the problem, because we want to swap the importance of type 1 and type 2 errors. So as I said, the probability of a type 1 error is often or generally denoted as alpha, the Greek letter alpha. The probability of a type 2 error is the Greek letter beta. And you have to be a little bit careful, because if I read papers and they say alpha equals this, you want to make sure alpha means statistics, but if they're in the section talking about statistics, it probably does. Beta is a little bit worse, because beta has a second interpretation in some statistics, which is the correlation of coefficient. Right? And so now you have to be careful to make sure you get it once. These two probabilities are inversely related in the sense, not inversely like one is one over the other, right? They behave negatively correlated. If I increase alpha, I tend to decrease beta. If I decrease beta, I tend to increase alpha. You can't really, in general, make both alpha and beta as small as you want for any sample size. Now, I can change my experimental design to simultaneously reduce alpha and beta by better design. But once I've chosen the design, the two, one goes up, the other has to go down, and they're largely tied by the sample size. Okay, so which in the court example is larger sample sizes equals more evidence, right? More data. That's what we're going to look at. Okay, so now coming back to this from a formal hypothesis, there are two critical, or a bunch of critical steps in our hypothesis testing, and there really are two hypotheses: the null hypothesis and the alternative. And you want to be a little careful when you're sort of phrasing these, and we'll talk about that on the next slide. But the procedure begins with the assumption that the null hypothesis is true. Okay, so this is part of how, when you're doing your statistics, how do I decide what's my null hypothesis? The null hypothesis is generally the opposite of what you want to prove. Why? Because you can't prove the null hypothesis. You can only reject the null hypothesis. So if I'm going to reject it, I don't want it to be the thing I want. So your null hypothesis is not, my algorithm is better than their algorithm. If that's what you want to prove, then don't make that your null hypothesis. Your null hypothesis is, my algorithm is equivalent to their algorithm. And then I can reject that. Now that doesn't, if I reject, my algorithm is equal to their algorithm. Right? So if I think of it, so I have A1 equals A2, that's my null hypothesis. What's my alternative hypothesis? So I can actually, so this is the issue, right? So this is why I said you have to be careful. The opposite doesn't always have the meaning you might think. The opposite of this is A1 not equal A2. That's pretty clear. But that doesn't show my algorithm is better than their algorithm. In fact, it might just show my algorithm is worse than their algorithm. It just says they're different. I don't know which one's better or which one's worse, right? So I can have a slightly different hypothesis. Right? I can say my hypothesis is that their algorithm is worse than my algorithm, in which case the alternative hypothesis becomes this. Okay? Unfortunately, this is very hard to do statistical test with. There's some that we can do, but most of the ones we're going to do are all based around this. A1 equals A2. Okay? And then what we actually have to do are two hypotheses. My first hypothesis is that A1 equals A2. I prove they're not. Okay. Now, if they're not, what's my next what's my hypothesis? Well, I can have the hypothesis that since they're not equal, A1 is less than A2. Okay, which when I reject that, I get A1 greater than A2. Okay. Now this turns out when we'll go through some slides. Right, this is often the sort of standard structure you end up doing with what you want to do to prove your algorithm is better. Okay, so even though I said there's a hypothesis, in my view, for most computer science experiments, there's two null hypotheses. The first is this. The second is the order. And it turns out for most of our statistical tests, there's a statistical testing difference here, but it's pretty easy to actually lump these together and pretend I'm answering that question in the first one. Okay? Because your hypothesis, that really is your hypothesis. Okay? So your goal is to determine whether there's enough evidence to infer the alternative hypothesis, the null hypothesis is false. Okay? And there are two possible decisions. The first is there's enough evidence to support rejecting this and accepting that, or there's not enough evidence to reject this. Okay? But that doesn't mean, and please never say in your papers, we accept the null hypothesis. The only thing you can say is we failed to reject the null hypothesis. And in that statement, we get to have three negatives. I failed to reject null. Okay? But all that means is I didn't have, it means one of two things. The null hypothesis is actually true, or it's not true and I didn't have enough data, and there's no way from your experiment to tell the difference. You can't say for sure which of those two occurred. Okay? So one fails to reject the null hypothesis. Okay, so when we talk about our null hypothesis, we have H0 and H1, or sometimes it's H0 and H hat. There's a couple of variations in terms of how people write it, but the null hypothesis often has this little naught or null at the bottom, and that's what you sort of tell what goes through it. So the null hypothesis will always state the parameter value equals the value specified in the alternative hypothesis. Okay. What did I write here? This makes no sense to me. The null hypothesis will always state that the parameter equals the value specified in the alternative hypothesis. Yeah, but that's not what I wrote on the slide, so ignore this. Right? This is saying we'll always equal the value specified in the alternative hypothesis. Right? The alternative hypothesis is a relationship between two things. Right? I don't know what I was thinking. Yeah. Please ignore that statement. So the null hypothesis will, base null hypothesis will always be that two things are equal, and then we'll reject that. Okay? Work our way through that. Oh, I see. I probably tried to write this slide twice and fix it up. Don't worry about that. So when we talk about the statistical testing, we're going to assume some model of and some amount of random noise. Right? The reason, if these are two numbers, and you ask me the question, is 3 less than 4? I don't need statistics. 3 is less than 4. The problem is, if I estimate something, and it's the average of this, and the average is 3, and this one has an average of 4, now you can ask the question, is that, even though the numbers are 3 and 4, is the average being 3 equal to the average being 4? Interesting, right? Now, if the average was the average of 3 numbers, then one of them equaling 3 and one equaling 4 is probably not statistically significant, because there isn't enough data for me to answer what would happen to those other numbers. If the numbers are uniformly random numbers chosen between -5 and 5, then maybe 3 and 4 might be significant. I don't know, I could run the test. But I'm very sure that if there were randomly chosen numbers between -1,000,000 and 1,000,000, then the averages of two samples being 3 and 4 would mean nothing if it was samples of small sizes, because the numbers have a huge variance. And we'll see where some of that comes into. So we say that if it isn't, given that set of data, we can then decide that we can reject the hypothesis in favor of our alternative hypotheses. And if they're not, we say they can't be rejected. You can't say that H0 is true, you just decide that it's rejected, which I think I've already covered. Okay. So a p-value, which is a common term you'll see in statistics, is the probability that our result, or the result being reported, between proportions or regression, however, there's lots of ways I could do it. But a p-value really says that the probability that the difference I've seen would occur randomly in a sample population. So if I say I'm going to reject this, I'm actually going to reject this with a, say, p-value 0.01. If I say that, then I'm going to say, given the data I've seen, the chance of an error where I accept this and I should not is less than 0.01. That's what we mean by a p-value in statistics. So this means if I ran 100 tests, this would happen randomly when, so is that a type 1 or a type 2 error? I'm accepting this and I shouldn't. Accepting this, so this is why I gave you the guilty verdict. Convicting a guilty person is type 1. That was the first one I showed you, right? So that's accepting, so that's rejecting the fault of the hypothesis. That's a type 1 error. Accepting this is a more common one, is a type 2 error with 0.01. So this is beta, p 0.01 for beta, because it's a type 2 error, accepting what it should be. So low p-values occur in practicality. Low p-values occur when there's low degree of compatibility between H0 and the observed data. So there's unlikely to be by chance, and if it's a very low p-value, you're going to reject the test if it's significant. Now, if I'm running a test at this level and I end up getting my actual, this is my goal, we'll call this star star, that's a common thing. If I actually get p of 0.017, okay, I'll measure my p of 0.7, then it's not significant at this level. On the other hand, it's a pretty low value of p. If I had said p equals 0.05, which is another common value, it would be significant, right? Sometimes people will say this is very significant, this is significant. Lots of terminology with it. One of the things that will often happen is this is actually assigned to you as an experimenter, that maybe I should run a bigger experiment. If I run this with 5 runs of my program and I get this value, I would tell you, you know what, I'm pretty confident that your results are significant. You just have too small a sample size, because 5 is a pretty small sample. Go run it 10 times or 50 times, and you can improve the statistical likelihood. On the other hand, this is still a point, let's call that, well, actually let's make it, we'll go back to the 0.5. So I actually got 0.5, right? Even if I get 0.5 with 5 samples, right, there's still a 5% chance that this is actually true. Your algorithm isn't any better. Okay, so a different way of looking at this, and this is, there's a, now I can't remember the term. It's related to a bias called the publication bias, but I think this is a selection bias. Imagine that you're working on a problem, and so are 100 other researchers in the country. And you're actually all doing pretty much the same idea, but you all have different random data. And you all go test your algorithm. So if I'm at p equals 0.05, 5 out of those 100 will get a result that is statistically significant and may publish a paper. 95 won't. But you will never hear about the 95 that failed because their experiment won't be publishable. So this is why it's called a selection bias or publication bias. The only things that get selected to show up are things that have passed that test. But if that test fails often enough and enough people do the experiment, then you'll get this. And I think we've seen that before. So high p-values really say you have a high degree of compatibility between H0 and the observed data. The association is likely to be by chance. Okay? It means don't reject H0, the test is not significant. Okay? It doesn't mean your hypothesis is false. Okay? If this p-value becomes 0.25, like, yeah, this could happen by random chance. So how do I reduce random chance? Okay, if this is 0.45, 0.8, forget it. There's really no relationship. What if it's 0.25? You might say, well, fine, I ran it with 10. Let's try it with 100. Okay? Now, a little bit of this we have to be careful of, because in computer science, we have to make sure that we're getting really meaningful experiments. Because if I run my program on the same set of data 100 times, if my program is deterministic, I'm going to get the same answer 100 times. That isn't random. Okay? If all I do is add a little bit of randomness to my program, such that it takes a random number plus its old answer, and the random number is a small random number, I can get 100 runs of my program. It didn't make it really random. Right? The randomness should be in the real data, not something that was artificially induced. Otherwise, these statistics don't apply. Okay? If you remember, I said this central limit theorem stuff only applies when the samples are random and independent. If they're not independent, this theorem breaks down and these statistics can go haywire. You have to be a little careful with that. So as I said, some various values, 1%, which is 0.01, 5% are pretty common, and we will generally refer to those. And in your paper, you should say at the p equals 0.1 level, p equals 0.01, whatever. So my recommendation is actually always give the p-value rather than just significant versus non-significant. But when I say give the p-value, I don't mean report the p-value of p equals 0.011325, right? I'm not looking for lots of digits here. I'm saying it's significant at the p.015 level. And if it looks like this, right, 0.0001, I would say that might be interesting to report. Reporting p equals 1 times 10 to the minus 23, right? The p-value no longer has any meaning at certain points, so you have to be very careful how to interpret it. And sometimes people will say, oh, that's great because it's even smaller, right? If I have two results, one with p equals 0.01, and the other with p equals 0.0000, right? So it's 1 times 10 to the minus 20, minus 10, right? Minus 100, right? This result actually isn't any necessarily worse than this result, right? Because at a reasonable level of statistics, chance of 1 in 100 or 1 in 1,000, these two are both significant. Higher p-values, smaller p-values, doesn't necessarily make it better, because it all depends on a bunch of other assumptions which may or may not be true, and under those assumptions, small changes in those assumptions, these two might switch places. Okay? A common one of these is, in fact, if I assume it's Gaussian, and I get way out here, right, then this is 0.01 or 0.0001, and 0.00001 might be out here. The problem is if the tail is actually not so flat, or worse yet, if the tail has lumps, then these p-values don't mean anything. Okay? Very often when you see really, really ridiculous p-values, it's because people have overemphasized the Gaussian model, and maybe they shouldn't have, because it's pretty far away. So you have to be a little careful as you play with this, right? And this is a quote that's sort of interesting, right? 0.05 is a convention, but it's not an absolute truth.
So you somebody
Sampling with replacements? So whether or not you get to consider them as, so again, this, to be honest, the rule for this isn't independence. That's just the simpler form of the central limit theorem. There are versions of the central limit theorem that have been proven with something called exchangeability, for which it's still true, and independent. So sampling with replication is not independent, but it is exchangeable, and so most of the things still apply to that data. Okay, so that's not a huge difference.
So how you must know the number of samples which
No, it is not true. It is a rule of thumb. In fact, I use the rule of thumb the other way. If you have less than 30 samples, I am dubious about your statistics. Okay? If you have less than 30 samples going on, there's good reason to not believe it's true. If I have more than 30 and my variance is low, see, this is the problem. 30 doesn't say anything about variance. But the central limit theorem for most well-behaved samples of distributions, 30 samples, this is a really good approximation after 30 samples to the central limit theorem. But that doesn't mean that it's true for your statistics. If I go back to this example, if I'm trying to estimate the mean, which is what the central limit theorem says, then 30 samples will give me a really good estimation of the mean. You flip a binary coin, whatever. But if I take a coin where the expected value, if this is 0.999, this is 0.001, those are the odds, and I flip that coin 30 times, okay, right, I'm going to get a value very close to this, everything will be fine. But if I flip a coin where I have one of two outcomes, okay, 0.501, or sorry, 0.5 and 0.5 is the probabilities, and the other is 0.501, 0.499. That is, it's a barely not biased coin. Then 30 samples won't let me distinguish between these two.
So
Right.
if I have a p-value, so I have to have two hypotheses. Because I have to consider, is it A better than B? So I have a
So we'll get to that in just a bit. So the standard way of answering that question is actually you do two tests, but you really only have, your real hypothesis is this. It just turns out to be expensive to test that, but it turns out it isn't with the right. For some tests it's easy, for others it's hard. So we'll get back to that. So, okay. But coming back to that, so if I talk about having a p equals 0.05 and its errors, right? The level of significance is called p.05. But we got to remember there really are two types of errors. Right? The first is the alpha or type 1 error. H0 should be rejected, but it's not. Right? So the alpha error is I convicted somebody I shouldn't have. That's the type 1 error. Type 1 is the worst thing. Okay? And then the other possibility is that it should be rejected, but it was not rejected. That is, the person was guilty and I didn't reject it. So but when I talk about my sort of p-values, there really are two kinds of p-values, right? So the decision for p-values is generally about should I reject it or not, right? But in the truth there's no difference. That gives me my error, right? So my probability of error for a type 1 error is 1 minus alpha. My probability for a type 2 error is 1 minus beta. Okay, that gives me those two definitions. Each of those definitions, when we talk about p, we're talking about answering the question, should I reject this? So the p-value is actually about the hypothesis about beta. P doesn't tell you about the other hypothesis, the type 1 errors. You need a lot of other statistics to get through it. I'm not going to cover how to do that, but if you're ever worried in your problem about that error, so looking at medical stuff, you have to worry about both type 1 and type 2 much more significantly than most computer science stuff, then you'll have to read another chapter of statistics, right? And this is one we already covered, so I'll go through this quick, right? We already talked about this. This is the same thing. If I have p equals 0.05 and I simply run 20 experiments, one out of those 20 experiments will randomly actually work if p equals 0.05. Right? So that doesn't mean this is where we ask the color of jelly bean, right? When we tested every color of jelly bean, one of them will not actually be meaningful. So now we're going to get into the actual processes for testing hypotheses. So there really are broken down into two big categories, parametric and non-parametric. And I'll briefly talk about a couple of these. The most common are the sort of z-test or t-test, which are extremely related. One-way ANOVA, there's multi-way ANOVA. I'll talk briefly about those. I'm not going to spend a lot of time on the non-parametric tests because for almost all of them, deriving the math is really, really difficult, and they're just analogs. So once you know what is the parametric test, you can just use the different software to do the non-parametric test in a similar way. You'll get different statistics. How to get to them is very hard. But the parametric ones are important because you need to understand the assumptions in them, because that's what decides whether or not you have to go to non-parametric. Once you understand the assumptions, you're going to say, I can use a parametric or I have to go to non-parametric. So parametric tests. involve population parameters or distributional assumptions, okay? And, for example, the mean. And they generally have some pretty stringent assumptions. Almost all of those are normality. You're going to assume normality, okay? And these are the examples. The examples we'll briefly look at are the z-test, the t-test, the chi-square test, and actually the f-test, or ANOVA. All of these assume normality. Going back to the central limit theorem, they're all going to look at the differences between means, or multiple means, okay? And that, in general, holds is based on stuff from the central limit theorem. But you have to be careful about that independence or exchangeability, and a few other things that can cause some problems. So non-parametric tests don't involve population parameters. They don't have probability distributions. They don't need independence, although they sometimes need a few weaker assumptions. They definitely allow you to deal with all kinds of things. By far the most common problems people run into about using the central limit theorem is it doesn't apply to data that doesn't live in a field, in a more formal sense, but it doesn't apply to data that isn't numeric data in the same space. So if I take a measurement of height, I don't care what the units are, meters, feet, yards, stones, that's weight, they're all okay. They're continuous measurements in the same space. If I ask a user a question on a scale of 1 to 5, how happy are you? Is the distance from 1 to 2 the same as the distance from 3 to 4? Might not be. If it's not, it's called ordinal data. And if it's not, if it's ordinal data, then this doesn't apply. The proof that underlies the central limit theorem assumes continuous, linear, organized data. If the answers are discrete values that are very separate, then the central limit theorem doesn't necessarily apply. That's by far the biggest time to say, oh, I have to go non-parametric, okay? On the flip side, you'll see lots of people that use it use ordinal data, okay? Because if I were to ask values and I assume that this distance and this distance are equivalent, then I'm really looking at regression. And if I did regression, central limit theorem does apply. So there can be a little bit of interpretation there. But this can deal with things that are ratios. Another place the central limit theorem doesn't apply is if the central limit theorem applies to x, it doesn't apply to 1 over x. Okay, so for every variable that's like this, one of the problems with this variable, this distribution, right? If x contains the value 0, right? I can have some distribution, right? And over here is 0. What does 1 over x do, right? Well, 1 over x has this really annoying property at 0, right? It's infinite. It's not bounded. Central limit theorem needs your data to be bounded. If it's not, it doesn't actually apply. So some things like that will occur. So an example of this would be like the Wilcoxon ranked sum test, the Wilcoxon rank test, and a bunch of other things. So the advantage of non-parametric tests, they can be used with all scales. They're easier to compute. Well, so they're easier to compute in some senses. The amount of computation is often less CPU cycles. They are harder to understand how to compute for many of them, so they're harder to compute. But with computers, they're a lot easier. So once you can figure out what function to call, it's okay. They make fewer assumptions. They don't involve population parameters. They apply over a wider range of data. The results can easily be as exact as a statistical test with parametric procedures, okay? But the disadvantages start with the fact that they may waste information. If I have a certain amount of data, and I'm trying to answer this question, and I use a parametric test and a non-parametric test, the parametric test is almost always more sensitive if it applies. So it will answer this question better and more often if it applies. So if I have ordinal data that actually does have this characteristic, that it's approximately equivalent, so I can treat it as though it was a regression problem, then parametric models are more sensitive to deciding what's going on. If the face is false, of course, that doesn't work, right? They can be difficult to compute by hand for large samples, okay, but with computers, as I said, it's actually pretty easy. They're definitely less widely known, so you're probably not seen these before. And they're less widely known in the sense that for Excel, the t-test is built in. The Wilcoxon test costs $100. Right? There's no built-in package. Now, if you use R or MATLAB or Python, all of them are built in and they're all free. But there's like just they don't get as widely used. They're not as widely known. Okay, so there's a couple of analogies we're going to do. These are the equivalents. So I'm going to spend a lot of time on these first three: the paired t-test, the two-sample t-test, and the ANOVA. Okay, their equivalents in the non-parametric form are the Wilcoxon signed rank test, the Wilcoxon rank test, and the Crucial-Wallace test. Okay, so once you understand how and when to use each of paired, two-sample, and ANOVA, you actually understand how to use Wilcoxon signed, Wilcoxon sum, and Crucial-Wallace test. You just say, oh, I can't assume, as I said, the most common thing for computer science is the numbers aren't equivalent. They're not a continuous number. They're discrete, and the difference between A and B in a survey and B and C in a survey are not the same. And as soon as that's the case, that A to B, B to C is not at all equivalent, then you have to use non-parametric tests. That's the most common reason you need them. So let's briefly, actually, why don't we go ahead and take a 5-minute bio break, and we will start into the t-test and stuff right after that. So a couple people came in late, but we got most people still missing too. But so for those who came in late, you're trying to give me your paper by Friday. I'll put it up on Blackboard so I can start giving you drafts. Right? I'm not grading you. The draft is I want you to turn it in. I'll give you comments. Right? There will be a grade for it, but it's pretty much you either have made enough progress now for me to call it a draft or not. I'm not grading its content, just that you made enough progress. The other thing is I'm giving out some extra bonus points if you go to any of our faculty candidates meeting of some kind. Doesn't even have to be one of the official meetings. If you want to go to breakfast with a candidate, and that's the only time you can make it work, let me know. We'll see what we can do. That will help make up some bonus points for missing journal entries for those of you who are behind. Okay, we'll be back by 5 after.